The next example is evaluate the inverse Laplace transform of e to the power minus 4s divided by s square plus 9. Okay, the moment we see something like e to the power minus 4s, we should remember that this will cause shifting of t. Okay, this will cause time shifting. So we remove this and we find out first the inverse Laplace transform of the remaining function, of the remaining terms. So first, let us find the inverse Laplace transform of the remaining terms. That is 1 by s square plus 9. So you remove e to the power minus 4s for the time being, and first find the inverse Laplace transform of 1 by s square plus 9. This is of the form sine. This is like the Laplace transform of sine 3t, except that one term 3 is missing in the numerator. So what can we do? We can multiply and divide by 3. So this is 1 by 3 inverse Laplace transform of 3 divided by s square plus 3 square. So this is inverse Laplace transform. So this is 1 by 3, and the inverse Laplace transform of 3 by s square plus 3 square is sine 3t. So the inverse Laplace transform of this is 1 by 3 sine 3t. So this e to the power minus 4s will only cause a shifting of the t, time variable here. Therefore, the inverse Laplace transform of e to the power minus 4s s square plus 9, this would be 1 by 3 sine 3t, and this t will be shifted to t minus 4. Here, since we have e to the power minus 4s, t should be shifted to t minus 4, and then it should be multiplied by u t minus 4. So this is equal to 1 by 3 sine of 3 times t minus 4 multiplied by u of t minus 4. So this is our final answer. Okay, this is fine. This is okay. So let us look at another example. That is, find the Laplace transform of a half sine shown in figure. So find the Laplace transform of a half sine shown in figure. And what is the figure? It's something like this. This is t, this is f of t. Half sine is something like this. This is t by 2. This is 0. Okay. So I have this figure, half sine. This is a half sine curve. And there are no further branches here. It starts at 0, it ends at t by 2. Then there are no further graphs. For t greater than t by 2, it goes to 0. Okay, so it was 0 for t less than 0, and it is again 0 for t greater than t by 2. So first question is, how do we express this as a function? Solution: the half sine can be expressed as the sum of two functions. As the sum of two functions, let us call it FAT and FBT. As the sum of two functions, FAT and FBT. This F of t, this is FAT plus FBT. And what is FAT? This is equal to, what is FAT? FAT is A. So the maximum amplitude is A here. A sine twice pi by t. T is the period and small t. U of t. This is the first term. If we plot this first term, what will we get? For t less than 0, it will be 0. For t greater than 0, it will be the sine wave. It will go like this. Sine wave when I never. Okay. Plus another A sine. Here we have twice pi by t t minus t by 2, capital T by 2. U of t minus t by 2. So this is FA, this FA is this, and FB is this. This is what? For t less than t by 2, this is 0. So till here, this will be 0. For t greater than t by 2, it is a sine wave like this. It will go like this. So you can smile chakrani. So you can smile chakrani. Okay, if I have color pen here, I can do it. Let me see if my green pen is working. Okay, okay. So the first graph, the first function, if I plot it, it will go something like this. Okay. Can you see the green curve? Then let me look for a red or a blue pen. Okay. Then this second function, it will go like this. Okay. So in this portion, there is only this function, but in this portion, we have the sum of these two functions. So if I take the sum of these two, the answer would be 0. If I take the sum of these two, the answer would be 0. So only for this portion, the function is non-zero. For the remaining portions, since these two functions are t by 2 out of phase, that is, they are out of phase by pi. When we superimpose these two, we get 0. Okay. This is like destructive interference. Okay, destructive interference of these two two functions from time starting from t by 2. So this curve, half sine curve, can be written as a sum of these two functions. Okay. So let us take the Laplace transform of this. Therefore, there is the f of s, that is the Laplace transform of f of t, that is equal to the Laplace transform of first term. So a is a constant, it can be taken outside. Laplace transform of sine 2 pi by capital T times t ut plus A times the Laplace transform of this term sine 2 pi by t small t minus capital T by 2 u of t minus capital T by 2. Okay. This is fine. This is fine. Okay. Now the Laplace transform of the first function, that is equal to a times this. First we take the Laplace transform of sine omega t. Sine omega t is omega, that is twice pi by capital T divided by s square plus omega square, that is twice pi by capital T whole square, plus a times the Laplace transform of second term. This is also twice pi by sine omega t minus capital T by 2. This is also equal to twice pi by t s square plus twice pi by t whole square e to the power minus t by 2s. So here, here we have shifting by an amount t by 2. So we have e to the power minus t by 2s. Okay, so this is the Laplace transform of the half sine wave. Okay, then one last example for today. Example. I have a function g of t. This is given as this is equal to 0 for t lying between 0 and 1. And this is equal to t minus 1 whole square for t greater than or equal to 1. So this can be written as t minus 1 whole square u of t minus 1. Okay, so this is t minus 1 whole square u of t minus 1. So first, if we neglect the shifting, then this is nothing but t square. So Laplace transform of t square is 2 by s cube, 2 by s cube. Therefore, Laplace transform of g of t, this will be 2 by s cube multiplied by the e to the power, the amount with which we are shifting, e to the power minus 1 times s, that is minus s. So this is the answer. Okay, this is the answer. Simple problem. So I think that would be all for today. I will stop the recording here.